I've got another problem up here. So here, I've got an equation for a level surface. X e to the yz equals 5. If I view that left-hand side as being the output of some function, so f of x, y, z is equal to x e to the yz, then I could say this surface is a level surface for f. Now, anytime I have a level surface, that equation is going to, at least at most places, implicitly define z as a function of x and y. It would also implicitly define x as a function of y and z, or y as a function of x and z, but most often we like thinking of z being the output and x and y being the input. Okay. So I can say this equation implicitly defines z as a function of x and y, and then I could try to find the partial of z with respect to x. Okay. Now, that is automatically going to be a 3C question. That you didn't have the tools to do in single variable calculus. But we could also do it this way. I could use implicit differentiation and the chain rule for functions of multiple variables, so that not only could I find this, but I could describe it in terms of f. Because if I just use straightforward implicit differentiation, I'm going to get a formula, but that formula isn't going to make any reference to this function. If I use chain rule, I'm going to be able to describe this in terms of f. So my directions here are to do that and then simplify. Now, just like with the last example, the first thing I'm going to do is completely ignore my directions and just do the implicit differentiation, because I want to see that the two techniques that we have are equivalent. So if I just took this equation, x e to the yz is equal to 5, and I were using implicit differentiation to find this, I would say, okay, let's take the partial with respect to x of both sides. And of course, when I'm doing that, I'm treating x as my input variable, or the independent variable. We're holding y as a constant, and we're thinking of z as being a function of x and y, but because y is a constant, essentially a function of just x. Okay, excellent. So when I take the partial on this left-hand side, I would say, okay, x is just a constant, and I'm multiplying that by, I'm taking the partial with respect to x, I'm sorry. So this would actually be product rule. My bad. X is not a constant, y is the constant. So I would be using product rule here. So I would be saying the partial of x is just 1 times e to the yz plus x times, now I've got to take the derivative of e to the yz. So I'm going to get e to the yz, okay, but then times the partial with respect to x of yz. Now y is just a constant, so I'll get that y. And then z is a function, so I'm getting the partial of z with respect to x. Okay, so that's the product rule on the left-hand side. And of course, the right-hand side, we're taking the derivative of a constant, so we will get a lovely 0. Quick check, z occurred just once in my formula, so I only wrote the symbol del z del x the one time. And now, of course, I could solve for it. I'm going to subtract that over and divide by this. So partial z, partial x, would be the opposite of e to the yz over xy e to the yz. As a general rule, I don't like to cancel things out of the denominator in my formulas because I don't want to lose information about any restrictions that I have. This formula is not going to be valid if x or y is equal to 0. But I know that e to the yz is never 0. So I can cancel that without losing any information. And so I can say this is just negative 1 over xy. Excellent. So let's write that down and clear some space. I want to make sure that we get the same result ultimately. But now I want to see what's its connection to this function f. So we said partial z, partial x, which is negative 1 over xy when we simplify it. But now let's try to get this using the chain rule. Okay. So a function of 3 variables would be spitting out a w value. So we're saying that w which, since we're on a level surface, w is constant at 5. If I wanted to, I could even write in w equals 5 to remind myself that it's a constant. Okay. That's a function of x and y and z. Okay. X, of course, is itself. Y is itself. But we're viewing z as implicitly being a function of x and y. Now, if I wanted to, I could say x is a function of x and y, and the formula doesn't involve y's. I don't find it necessary to write that in. Okay. All right. Now, if I'm looking at the partial of z with respect to x, I'm looking at the x's. I don't really care about y because I'm going to be holding y constant. So I'm going to be concerned with all of the paths that connect w to x, which are these paths here. So even if I had said x is a function of x and y that doesn't involve y, I wouldn't care about that path. I only care about connecting these things to x. Okay. Now, I do need to be very careful. Notice x occurs on multiple levels here. It would be absolutely wrong to write this as the partial of w with respect to x, because w connected to these guys, that's what I mean by the partial of w with respect to x. Remember, the rule is when you're using the names of the variables, you're looking at the entire relationship between those two variables, not just some piece of it. So, when I have, as I do here, that some variables occur on multiple levels, it is necessary that I say this part of the diagram is talking about the function f. I can't here use f and w interchangeably because f makes it clear that I'm talking about the top half of the diagram. W has a relationship to the middle and has a relationship to the bottom, and I wouldn't know which I was talking about. Okay. Now, if I write del w del x, that does have an unambiguous meaning. That is looking at all of the ways in which x affects w. So that's relating w to the x that's on the bottom level. Okay. It is not just this part of the picture. This part of the picture would be the partial of f with respect to x to indicate that it's just dealing with that part of the picture. This would be the derivative of x with respect to x, which is just 1. If I had written that x depended on x and y, I'd write that as a partial derivative, but it would still be 1. Okay. All right, and then this is going to be the partial of f with respect to z. Okay. And this will be the partial of z with respect to y. Okay. Now, that's a partial because z is implicitly a function of both x and y. Okay. And I'm just consistently using f up here. It wouldn't be ambiguous for me to write partial w, partial z, because this is the only place that z occurs here. But that wouldn't help me in my directions, because I was trying to look for the relationship between this thing and f. So I want to have these things both defined in terms of f. And so now I can say, okay, that's the partial of f with respect to x times 1. That's the product of all the derivatives along this path, plus the partial of f with respect to z times the partial of z. Whoops, I wrote y. That should be with respect to x. Okay. Partial of f with respect to z, partial of z with respect to x. Okay. Notice, this is the thing I'm trying to solve for. I was trying to describe it in terms of f. This piece here and this piece here have an f in them. That extra piece, I know what it is, because I wasn't working with the entire function. I was working with this level surface. W is 5. It's constant. Any derivative of a constant is always 0. So this is 0 equals partial f partial x plus partial f partial z del x. And now I'm going to be able to solve that for the partial of z with respect to x. I'll just subtract over this term and divide by the partial of f with respect to z. So we'll get del z by del x is the opposite of del f del x divided by del f del z. Of course, that's if this is not 0. This will be undefined if this is 0. Okay. But if this is not 0, and it's understood when you write a formula like this, of course we know it's undefined if it's equal to 0. It doesn't hurt to just remind ourselves of that rule. Okay. So this is describing it in terms of f. Now we were asked to simplify. So let's actually calculate what these are, and we know what we should be getting. We should be getting the same formula we got when we just did the implicit differentiation. So I can say this is going to be the opposite of the partial of f with respect to x. Well, that's treating y and z as constants, so e to the yz would be a constant. Notice when I'm doing this, I'm not thinking of z as being implicitly a function of x and y. Okay. Partial of f with respect to z, now x is a constant, times the derivative of e to the yz is going to be e to the yz times y. And again, I usually don't like to cancel things from the top and the bottom lest I lose some information about where things are undefined. But since e to the yz is never 0, I can cancel that. I get negative 1 over xy. Oh, yeah, it worked. Okay. So, if I give you a question on implicit differentiation, if I give you a level surface, and I say, use implicit differentiation to find the partial of z with respect to x, you could do it either way. Both methods, just the implicit differentiation we did initially, and this method, which involved the chain rule as well, both of those used implicit differentiation because they were treating z as implicitly being a function of x and y. But be prepared, I might ask you to use implicit differentiation together with the chain rule for functions of multiple variables. That's asking you to do it this second way. Okay. You are responsible for knowing how to do that, so to derive this formula and then use it to simplify if I ask you to do that. Okay. You are not responsible for having this formula memorized. So in your textbook, this formula probably has a number. Some of the homework might say use formula, whatever the number is, to do this problem. Interpret that as derive formula, whatever the number is, and then use it to simplify the problem, because that's what I would hold you responsible for. And what's nice about that is it gives me a relationship between this derivative and the function that's defined, that it was a level surface for, which I don't see that relationship here, but I absolutely do see that relationship here.